Good morning, good afternoon, good evening, everyone. Welcome to day 2 of this ocean session by the Copernicus Marine Service, focusing on the future of the high seas. I'm Marine Delorme, Capacity Development Officer at Mercator Ocean International, and I will be guiding you through today's session. Today, we'll explore how operational ocean data made available by Copernicus Marine can be accessed and used for topics like high seas governance, ecosystem assessment and monitoring, and biodiversity habitats. Before we begin, here are some house rules to make sure you enjoy this session to the fullest. So please don't use the chat box on your right-hand side. It's only here for greetings, so don't use it for questions. It's for also sharing links with participants throughout the session. If you have a technical or content-related question, we invite you to use the dedicated Q&A section. You can scan this QR code on the screen or click on the Q&A button at the top of your screen to ask questions to our speakers. We'll have a Q&A session at the end of each presentation. And while you're on this page, you'll also see there is a poll section. So feel free to fill it out anytime during the session. It's for you to let us know what you thought of the session. And we will also send you a link to the survey after the webinar, so you can fill it out later if you prefer. We also encourage you to visit the guidelines and resources section of the event website. You will find useful links to Help Center articles to several interesting parts of the Copernicus Marine website, as well as links shared by our guest speakers from the first day and today. Just a reminder on how to access the tutorials we'll be presenting today. So you need to go to the tutorials tab of the event website. And from here, you can download the files or access them directly on the Copernicus Marine Binder Hub for Python and R. And I also encourage you to explore our 3 YouTube tutorial playlist, where you can find videos developed for both previous events and this event. So a bit about the agenda for today. We will have first a presentation from Leila Fabre from Mercator Ocean, who will present the Copernicus Marine Toolbox. And then we will have a Python tutorial presented by Alexandre Omrin from Noveltis, focusing on risk mapping and the NBBNG impact assessment. Then we will have a short coffee break, and we will go to Daria Andrievskaya, who's also from Noveltis and who will demonstrate a QGIS tutorial focusing on seasonal tuna habitat in the high seas. And we will end the session with an R tutorial presented by Simon Millet from Noveltis that will focus on the Rockel Seamount, which might be a prospective high seas marine protected area. So without further ado, let's start with our first speaker, who is Leila Fabre from Mercator Ocean, and who will present the Copernicus Marine Toolbox. Leila, can you hear us?
Yes. Hello, everyone. I'm just going to share my screen. So today, I will introduce you to the Copernicus Marine Toolbox, which is a free and user-friendly tool designed to interact with the Copernicus Marine data store. And this tool allows many possibilities with its 4 main functions: login, describe, get, and subset. With the login function, you can create an encrypted file that will contain your credentials, so that you won't have to write your username and your password each time you need to download data. With the describe function, you can explore the Copernicus Marine catalog, and you can retrieve the products and the datasets metadata. With the get function, you can download the original files as delivered by the producers. And with the subset function, you can download the part of a dataset that interests you. So it means that you will extract the geographic area of your choice with the variables you need, the depth levels of your choice, and the temporal extents you need. The advantage of the toolbox is that with this tool, there is no limits for data volume and bandwidth, so you will be able to download data with a significantly improved performance. The toolbox can be used in a command line interface, but also with Python. During this presentation, I'll show you how to use the toolbox with both ways. And I'll show you examples of requests you can use to download the data, access the data. So you will see how quick and easy it is to use the toolbox. For the command line interface, I will be using the Mamba's Mini Forge prompt. Sorry. And to work with Python, I will be using Visual Studio Code. Okay, so let's start at the beginning and let's go to the Copernicus Marine Help Center. So this is where we have all the articles about our different services. To access the articles about the toolbox, you have to click on Copernicus Marine Data Download. Then you scroll down and you have the section for the Copernicus Marine Toolbox. So in there, we have 33 articles that are sorted in 4 sections. In the Getting Started with the Toolbox section, you will find all the information about the toolbox, how it works, how it can be used. You have this article, Installation, that I highly recommend you to check if you want to install the toolbox on your machine, because it explains how to do it properly. And if you don't want to install it on your machine, you always can use the executable file. In the main features section, you will find articles that gives you the necessary information about the different functions of the toolbox for the command line interface and with Python. In the use cases, you will find articles that show examples of specific use case with the toolbox, for example, how to get data for a recurring period. But there are also articles that explain how to use the toolbox with other softwares such as R or Julia. And then in the last section, you will find the articles you need if you have a question about the toolbox or if you encounter an issue. You have this article if you want to report an issue to the team or if you want to request a new feature. And with this last article, you can see the past and future evolution of the toolbox. Okay, for the sake of this presentation, we are going to pretend that everyone has installed the toolbox by following the steps from this article. So it means that we have installed the toolbox in a dedicated, isolated Python environment. So from there, the first thing that I will do is open a command line interface and activate the environment in which the toolbox is installed. So as I said it before, I will be using Mamba's Mini Forge prompt. Right now, I'm on the base environment, so I have to activate the environment in which I have installed the toolbox. So my environment is named CMT230, and now it is activated. To check if the toolbox is correctly installed, we can just call the package and then specify that we want to check which version is installed. And then with this line, we note that the toolbox is correctly installed and that we have this version 230. Okay, so let's start with the first function of the toolbox, which is the describe function. With describe, just to remind you, you can explore the catalog of Copernicus Marine and retrieve the products and dataset metadata. So the first line I want to show you is this line. I call the package, I write the name of the function, and then I had a -- help. With this line, you can see what are the options you can use with describe. So you can see now we have a list of options on the left and their description on the right. And here you have some examples of describe requests. We are going to write describe request together to search which products and data sets IDs contain chlorophyll data in the data store. So we just have to call the package, write the name of the function. To filter what we want to search for, I will use the contains option. And I will add CHL that correspond to the chlorophyll variable. And then I will use the return field option to specify what I want to see in the output to avoid having too much information. Return fields. Return field. And I want to see in the output product IDs and the dataset IDs. I will save the output in a JSON file. I will call JSON. Okay. And then I can just run the request. So the toolbox is fetching the catalog and the products. And you will see that just in a few seconds, we should get our file. Okay. Okay, done. So if I go check my data directory, there is my JSON file here. And if I open it, we can see a list of the product IDs and their data sets that contain CHL chlorophyll data. So you can see that we have many data sets that have this kind of data in our data store. Okay, so that's it for the describe function. I won't show more during this presentation, but you can check the options available or read the article in the Help Center. Okay, now the next function I want to show you is a pretty useful one. It's the login function. With login, just to remind you, it's a function you can use to create an authentication file on your machine so that you won't have to write your username and password each time you need to download data. So this is a function that you have to use only once, and then you can forget about it because the file will be stored on your computer. So I'm going to show you the line. You have to call the package Copernicus Marine, and then you write login. Then you click on enter. You will be asked to write your username and your password. Be careful because the writing of the password is hidden. Then, so I already have a credential file on my machine because I already used the login function, but I'm still going to override it to show you. You will get this message, credentials files stored in. You will have your credential file stored on your machine. And then but you will see it during this presentation. I will download data, but I won't be asked to write my username and my password because I used the login function. And that's it for this function. That's the only thing you can do with it. Now, the next function I wanted to show you is the get function, with which you can download the original files as delivered by the producers. So let's check the options available with get. Same as before, we call the package, we write the name of the function, and we add the help argument. And this time you can see that the list of options is longer. So there are many possibilities, but the only mandatory option is dataset ID because we need to specify from which dataset we are going to download the data files from. We are going to write a get request together. So the first thing that we have to do is to choose a dataset. So I'm going to go to the Copernicus Marine data store, and I will use this product because I know that it contains chlorophyll data. I go to data access, and here you see I have the list of all the data sets available in the product. And in this presentation, I will be using this dataset. It contains chlorophyll data in a daily resolution. I can use this button here to copy the dataset ID. And I go back to the prompt. So to use get, I call the package, I write the name of the function, I have to write the name of the mandatory option, and then I copy the dataset ID. I could run the request as it is right now, but it means that I would download a lot of data because I just want to show you. This dataset contains data from 2021 to 2026. So we're not going to do that during this presentation. I will use the filter option with which you can filter which files you want to download. So filter, and I will download only one file for 1 day of data for the 3rd of December 2025. And then I can just run the line. So the toolbox is giving some information about the dataset version and the dataset part that is used. Okay, and now the download is done. We have the information that tells us how many files were downloaded, so 1. And if I go check the data directory, I have a directory that with the dataset ID, the product ID, the dataset ID, the year, the month, and my file for the 3rd of December 2025. So, sorry, this is my cat. So this is how it works. So there are many other options you can use with get. So I recommend you to explore this function and to read the article in the Help Center. And now I want to show you the subset function. So subset, as I said it before, with it you can download the part of a dataset that interests you. Since we've been working on the command line interface since the beginning, we are going to switch and work with Python. You will see that the syntax is a bit different, but it's kind of similar. So let's open Visual Studio Code, but you can use the editor of your choice. I open a new file as a notebook. If you use a notebook, be careful to use the correct kernel that correspond to your environment. Okay, and now I'm all set. I can just import the Copernicus Marine Toolbox package to use it. Okay, perfect. So let's see together which options are available with subset. So this is the equivalent of the line I was using on the command line interface with the help argument. To do that on Python, you have to call the package dot the name of the function, and then you add the question mark. And then if you run the cell, you will get this list of options you can use with subset. We are going to create a subset request to download data together. But if you've never used the toolbox, if you're a beginner, the best way to do that is by using the subsetter, and I will show you how to do that today. So I will go back to the data store, and we are going to use the same data set as before. To access the subsetter, I have to click on the form button, and we are on the subsetter. So basically, with this web page, you can download data directly. You just have to select your different parameters and click here. But with this online web page, there is a size limit. So you can also use this web page to create a request for the toolbox. So we are going to see that. I'm just going to select the different parameters. I will download 3 days of data, and I'm not going to change the depth range. And to create a request for the toolbox, I just have to click on the automate button. I will have a request created for the command line interface and for Python. So as we are using the toolbox with Python, I just have to copy this request. I go back to my code editor and I paste it. I'm just going to remove this line because we have already imported the toolbox. And the request can be run as it is right now. I'm just going to specify the name of the file with the output file name option. Okay, and now I run the request. And you see in just a few seconds, my data is downloaded. And if I go check my documents, I have my data file right here. Now I will present you the last two functions of the toolbox, open dataset and read data frame. These are very useful functions because with them, you can open the data remotely without having to download them. These two functions can only be used with Python, so you can't use them on a command line interface. Okay, let's check the options available with Open Datasets the same way as before. So these are the options. In fact, if you check them carefully, you will see that they are very similar to the options of the subset function. And to show you how similar they are, I can copy the subset request, paste it in a new cell. I can just replace subset with open dataset. I will just remove output file name because there will be no output as we are opening the data remotely. And I'm just going to save the data in a variable. Okay, and then I can just open my data remotely, as you can see. I can use them as I want. I can manipulate them. And if I'm done working with the data, I can always download them with the to netcdf option. And then I can give a name to this data like this and download them very quickly in my documents, as you can see here. Read data frame works the exact same way, except it opens the data as a data frame. So it is pretty useful if you want the data in a CSV format. Okay. You will see now we can open the data and see them displayed in a data frame. And once you're done working with the data, you can download them in your file with the to CSV option. Like this. And we can see them here. Okay, so during this presentation, you've seen all the functions of the toolbox. You have to know that not all the data sets in our data store are available with the subset service. It means that not all the data set can be used with the subset function, the open dataset function, and the read data frame function. In fact, if we go to the user notification service, so this is where you have all the notification for the incidents, general notification, maintenance, and so on. In the incidents section, there is this notification, datasets in the process of being formatted for the service subset. You have a list of all the datasets that are not available with the subset service yet. So we update this notification as soon as the datasets become available. So yeah, you can check it regularly if you have datasets that interest you. Yes, and if you have a question about the toolbox, something you're trying to do but you don't know how, first I recommend you to check the help center that I showed you at the beginning. But you can also open this widget here and click on messages. And then if you click on ask a question, you will be able to talk with Blue, our AI chatbot. It has a lot of knowledge on the toolbox and on our services. But if its answers are not satisfying, you can request to talk with a human agent, and then Blue will be passing the conversation to us. So we can help you. I'm now done with this presentation. If something was not clear enough, or if you have a question, do not hesitate to ask your questions, and I will try to answer them my best. Thank you.
Thank you very much, Leila, for your presentation. We have a few questions for you. So I will share my screen. Okay, so the first question is the toolbox free?
Yes, it's completely free, so go use it.
As all the services made
Yes,
available by
yes, it is.
Copernicus Marine. Uh,
Yes.
Everything is free, so enjoy it. Next question is in the filter option, if I want to download the full year, what should be the script to use, please?
You would have to write the year, just the year instead of specifying the month and the day.
Okay, thank you. Next question. So yeah, this one I saw appear and disappear. So just in case I put it back, are you running a Python shell locally on or on the Copernicus Marine host?
Uh, During my presentation, I was working locally, but I think that someone might work, no, mine on Binder Hub later. No,
Yeah,
ah,
the tutorials will be available on the Binder Hub
that the
if you
users
want to.
can use. No,
Absolutely, yeah.
okay.
You can access the Binder Hub um, by clicking on the button on the tutorial page, and once again, it is free. So don't hesitate to run the notebooks on there. But you can also download the notebooks if you prefer to run them on your machine. So it's up to you. Next question, please, is can we run Java or R rather than Python in Copernicus Marine environment?
The toolbox can be used with R, if that's your question. We have articles in our help center that explain how to do that. For Java, I don't really know, sorry, but you can contact us through the chat and we will look into that.
Okay, thank you. Are there any alternatives besides Mamba?
Yes, so there is Conda, Mamba. You can use, sorry, just going to check the installation article. There is the installation using Docker. You can use the, I don't know how it is called, UV, something UV, I think it's the tool you can use. And you can install with pip, but we don't really recommend just using pip. So yeah, Mamba, Conda, Docker, this is what is mentioned in the article, at least.
Okay, and we posted the link to the article collection on the chat, in the chat, sorry. So don't hesitate to have a look at all these really helpful articles if you work with the toolbox. I think they could be really helpful for you. Okay, and I think last question. Oh no, we have another one. Will Copernicus Marine install AI agent for helping construct Python code snippets for? I don't know if it's something you have an answer to, Leila.
Uh, there won't be, I don't, for now, I don't know if there will be an AI agent for that, but Blue, our AI chatbot right now, can help you create your requests for the toolbox. So you might want to check that. It is pretty useful. A lot of users ask it to help with their Python code for the toolbox related with the toolbox.
Great. Yeah, Blue knows a lot of things, so
Mm-mm.
don't hesitate to use it. And I think last question is it possible to download data using selection data patterns in different locations at the same time, or using different patterns than rectangular or square ones?
Okay, so for the second part of the question, using different patterns than rectangular or square ones, uh, it's not possible. You can, I think you can specify. No, you can just download the data in a rectangular or square shape for now. And for the first part of the question, yes, you can download data in different location. And I think we have an article that explains how to do that in the help center. So you can go check that. But if I'm wrong, if I imagine this article, you can contact us and we will help you to create this script if you want.
Okay. Thank you very much. Yeah, okay, let's do just one last question and after this one we'll end the Q&A session. Do optional parameters from X-ray original functions work with Copernicus Marine Toolbox, like concat characters in open dataset?
I'm sorry, I can't answer this answer. I would have to try it before. Uh, I don't know, sorry.
Would Blue know the answer to this?
I think, I think.
Okay, great.
But
Well,
yes, you can contact Blue, and then if it's not answering your question correctly, contact us, and we will take the time to look into this question.
okay, well, thank you very much for your presentation, Leila, and for answering all these questions. We will now go to the next speaker for today,
Goodbye.
who is Alexandre Omerin. So let me stop sharing my screen. So Alexandre will present, we'll do the demonstration of a Python tutorial. Alexandre, I can see you, so the floor is yours whenever you're ready.
Thank you, Marine. So hello, everyone. I'm going to start sharing my screen and we'll be able to start the presentation. So you should be able to see it. Is that okay?
Yeah, all good.
Perfect. So hello, everyone. I'm Alexandre Romain from Noveltis, and I will present to you a case study on the BBNG treaty impact assessment in Python. So our case study today will be a risk assessment and risk mapping in the high seas. So the interest for this case study is that, so as we've mentioned in the topic of this training session, so the Biodiversity Beyond National Jurisdiction Treaty concerns areas beyond any national jurisdiction in the high seas. And it means that when planning activities there needs to be a framework in order to conduct environmental impact assessments to predict impacts, evaluate potential impacts of planned human activities. And we will try to provide some tools to do that in this notebook to predict so impact of potential human activities in the open ocean. And we will do that by using currents data in order to establish an environmental reference to evaluate the risk of pollutant diffusion, for instance, in the area. And we'll do that with Python. So here are some sections to set up the notebook, the coding environment to conduct the study. So this notebook uses very commonly used Python libraries. You're probably already familiar with them if you've worked with Python before. We'll be using NumPy, Xarray, Matplotlib, and CartoPy. So NumPy is one of the most common packages to process ND arrays of data. Xarray is the package to process netcdf data, which is the format of the Copernicus Marine Service files. And then Matplotlib and CartoPy are used to draw the different maps and graphs in order to visualize our results. All these libraries should be pre-installed if you're using the current Binder Hub that is hosted by the Copernicus Marine Service. So just make sure that you have the Python 3 kernel activated, and you will be able to import the libraries at the first try. But if you're working in your environment, you just need to install those libraries to make the notebook work. Here's another setup section. Here we're just defining a very quick function that we'll be using several times afterwards in the notebook. It's just a function that draws the basic geographical features of the maps that we're going to draw. So you can just see that it draws the coastlines, the borders, the grid lines for the coordinates, and then zooms in on the area of interest that we are looking at. So we just need to set this up so we can use it in one line for each map that we're going to draw afterwards. So now that the notebook is set up, here is a brief section on the dataset that we're going to use. So as I've mentioned in the introduction, we are going to use currents data, but also temperature data to simulate pollutants propagation in the high seas. So both those variables will be available in this dataset, which is the Global Ocean Physics Reanalysis. So it's one of the Copernicus Marine Service products that covers the entire globe, which is why it's interesting to use because that way we are able to monitor any area in the ocean. So you can click on the link to visit the dedicated page in the Copernicus Marine Service website and have a closer look at the different variables that are available. So here's a brief summary. So it's a product that is based on a model called NEMO, which assimilates also real-world data from the European Center for Medium Weather Forecasts. And in our case, here are the main information that are going to be useful to us. So just know that it has about an 8-kilometer resolution. We are going to retrieve the two components of the currents and also the seawater temperature. We're going to retrieve only the surface level. We have several depth levels available, but in our case study, we are only going to retrieve the surface. So the product is available in many temporal resolutions, and we're going to use a daily product. And we have a more than 30-year coverage, but in our case, we're only going to retrieve a 6-month period in 2024 to keep files with a manageable size. But of course, if you want to know more about the product, you can visit the links for the user manual or also the quality information document if you want to understand a bit more about how the product was built, what exactly are all the variables contained within it. There is more, of course, than temperature or current. We also have salinity, for instance, mixed layer thickness, for instance. So we're only retrieving a small portion of the product for this study. And finally, for this setup, here is a brief section on the Copernicus Marine Toolbox that was presented to you in the previous presentation. So it's the same framework. So import the Copernicus Marine Toolbox, make sure that you can log in so you can request data without having to enter your credentials every time. And then we will use a subset function that has been presented to you before this presentation. So now we're going to build our request for the data set. So here are the parameters that we're going to set up. So first, as I've mentioned, we're only going to retrieve 6 months of data to have a manageable file size. So here's January to June 2024. It's an arbitrary choice, but this is what we're going with in this presentation. Here we're setting up a very small depth coverage in order to retrieve only the surface level, which is at about 0.4 meters below surface in this product. And finally, we are retrieving an area here, which is located in the North Central Pacific. So we're making sure that it is far from any national jurisdiction, which is the key topic of this presentation, of course, to comply with the BVNG constraint. And here is just a brief map to show you where our area of interest is. So you can see that I'm just plotting here the coordinates that I've defined here. And you can see that our area of interest will be indeed in the middle of the Pacific. And here you can see that we are using all those parameters that I've set up in this cell in the subset function of the Copernicus Toolbox. So here is the ID of the product. So in order to retrieve it, remember to go to the dedicated page, data access. And here, as I've mentioned, we are retrieving the daily data set. And if you go to form, you will find the variable names here that we want to retrieve. In our case, as I mentioned, we want the 2 water velocity components and the seawater temperature here. And you can see the variable names are indeed copied here and the ID here. So once you've executed this cell, it takes only a few seconds, and you will see that in your data directory in your Jupyter, in your hub, the product will be available. And now we're ready to open it and see what it contains. So here is our product open within the notebook. You can see that we have 4 dimensions: time, depth, latitude, and longitude, and our 3 variables. You can explore all of the variables clicking on the page icon here. One of the most useful things in this additional metadata is, of course, the unit of the variable. So here for the temperature, we can see that we are in degrees Celsius. So we won't have to perform any conversion from Kelvin, for instance. And here we have indeed the depth dimension that has only 1 index because we have only retrieved the surface level. This is not useful to have 1 dimension with only 1 index, of course. So if we use the squeeze function, we can just remove it. You can see that it still appears, but now our dataset has only 3 dimensions. This will ensure that we have a smoother workflow in the later computations, and that this additional dimension will not generate any errors when doing later processing. And finally, for the pre-processing, we can compute the total velocity of the water by combining the 2 components, northward and eastward. And now we have a dataset with a total speed variable calculated from the 2 currents components. So here is a quick figure to show you the average total speed over the entire period in the area. So we can see the small islands that we have here. And here's the map of the average current field, which is our first oceanic roadmap. And we can see that in the north we have weaker currents than in the south. So you can see that it shows how water moves over time. And here is the average total speed, and we can also calculate the standard deviation of the total speed, which will show us the variability of the water. Whoop. Looks like I've had an error. Okay, it looks like I have an error in my notebook. Okay, I think I just had to restart everything, so now it's fine. So as I've mentioned, here's the map of the standard deviation of the current speed. And we can see that it is in areas where we have the strongest current that we also have the most variability. So it probably means that in those areas, there is much more turbulence than in the northern areas here. The next section is about frontal dynamics. Here we are moving towards temperature data to calculate gradients. So when you calculate gradients in these oceanic areas, so here's a function that computes that for our data set. And I'm going to visualize it right away. So here are the gradients of temperature, the variation from south to north and from east to west. And we can see that the temperature gradient has the shape of many filaments, like we can see here. And this complex web shows that actually here where the gradient is strong, those are actually biological hotspots because this shows where the nutrients are traveling. And so that also implies that any disturbance near those more colored areas probably have more impact on biodiversity than in the darker areas here. And so for the most interesting part of the tutorial, here is the part where we simulate the propagation of, here it will be particles, but it can be pollutants, for instance. What we're going to do is that we're going to release fictional particles on a spot here in the area and see using the currents data how the particles travel in the ocean over time. So we're going to release the particle at a specific point. Here are the coordinates that we are defining, that we are storing here. So the place is actually, if we look at the map, so 165 degrees west here and I think 28 degrees north. So we are here at this spot. So we are very near some strong filaments here, for instance, from stronger thermal fronts. So we are very likely to see movement in this area. So we are releasing 200 particles spread around this point. Here is the amplitude of the spread. And here's a function to generate the particle. So with some random spread around the starting coordinates. And if we look at our particle release, so here's the point I had shown you before where we're releasing particles. And if we zoom in, we can see that we have some randomness in our particle spread at the point of release. And finally, here is a function that we're going to use to simulate the trajectories of the particles over time. So it's quite a big cell. I'm going to go quickly on what each function does. So here is a function that goes to the particle position and retrieves the current velocity values from our data set. So you can see that it returns the two components, vertical and meridional. Here we have the function that updates the particle trajectory based on the current data. So you can see that here those two variables are the delta of position that will be applied to the particle. Here is a function that applies some randomness to the displacement of the particle because, of course, our model has a big spatial resolution and doesn't necessarily capture all these smaller phenomena that can happen in the ocean. So we had some turbulence to simulate that. We are not going to use it right on the first try, but we can. It's an option to use to add this randomness. And here is the main function that uses all of the previous functions. So it just takes as argument the particles, asks you if you want to add the random diffusion or not. And here's the diffusion coefficient that can be stronger than that. And it updates the trajectory over time using the current data. So we're going to do that once without using the random diffusion, just to see where our particle travel without any randomness. And we can see that starting from this point, most of them travel east first, and then we have some divergence with a lot of particles going this way over the 6 months of data, and a few of them going the other way. You can see, especially here, that it quite well follows the thermal fronts that we have in the background. And so this spaghetti view can be enhanced then using the random diffusion, as I've mentioned. So this is what we do here. We add here the diffusion with the randomness, with the coefficient by default at 10. And here, if we look at the result, we can see that the trajectories are a lot more chaotic, and so reach more air, have a more wider grasp on the area. So this means that when conducting environmental impact assessment, this randomness has to be taken into account, because it can imply that a wider area than predicted can be affected, let's say, by human activity or the release of pollutants in the water, for instance. So this can be important to simulate when conducting such studies. And finally, in the last section, we're going to enhance this view and produce probability maps. So here, what we're going to do is to use the trajectories to plot a probabilistic heat map. So for each pixel of the grid, we are going to count how many times we have a particle passing through. And so, of course, when plotting this map, the pixels where the particles will be the most present will appear in a more red color, and the pixel with not a lot of passage will appear with a lighter color. And if we look at the results, so from our trajectories from before, we can see that, as predicted, we have a lot of passage near the point of release, of course. We have some strong here probability to have diffusion of pollutants, for instance, especially here in this south to east trajectory over the time period. And then you can see that we have it traveled almost over our entire area of interest. And finally, I'm just going to show you how those results can differ depending on the time period that we choose to study potential impacts. So here I'm just going to split the data set between winter and spring. So I had from January to June. So here I'm going to select January, and for a second subdata set, I'm only going to select April to have a separation between winter and spring. And I'm going to perform exactly the same operation. So simulating trajectories, this time only over 1 month of data, of course. So we'll have smaller trajectories, and see how our probabilistic heat map look like. So here is the one from the winter dataset, so from January. And we can see that from the initial point of release, the particles tend to travel southeast. You can see that it still follows here. You can see underneath the thermal front here that's quite well, nicely positioned. But if we look at the spring dataset, gonna take some time, we can see that we have a totally opposite dynamic. So from an initial point of release, it goes northwest here, which quite shows that when planning activities in the high seas, it is essential to take the operational timing into consideration for the environmental management. So that's what, for example, project planners should be aware of under the BBNG treaty, for instance. Okay, so we're reaching the end of the training. Here are a few exercises if you want to go further in the analysis. So first, of course, you can rerun the entire simulation using another point of release here. You can change the coordinates of this initial point. You can also play with the randomness coefficient to have even more chaotic trajectories. And of course, you can retrieve more data to, for instance, extend the simulation to a longer time frame or to another period. You can also explore other depth levels. So we had the surface level, but if we look at the original data set, I think we have, yes, 50 depth levels available. And I think if you look at the surface level, we can go up to 5,000 meters. So there are plenty of room to explore here. So feel free to do that. And thank you very much for your attention and feel free to ask me any question. Thank you very much.
Thank you, Alexandre. We indeed have a few questions for you. So let me share my screen. I'll just take it from you. Sorry.
Yes, sorry, of course.
No, that's fine. Okay, so the first question is it always mandatory to use the squeeze function when focusing only on surface water? What would be the impact on data quality?
It's not mandatory, but it's highly recommended, I would say. The point of using this is to just remove the remaining depth index that we had when we first opened the dataset. It's better to remove that because then afterwards, when you're trying to manipulate the data and process it, you don't have to worry about this remaining dimension anymore. So it will prevent you from having errors in your later computations. So this is why, personally, I highly recommend to use that to clean the data set before manipulations.
Okay, thank you. Next question is it possible to simulate bodies instead of particles with mass or drag? I'm thinking about floating marine mammal carcasses, for example. It could also be mines in the case of the Black Sea, for example. Thank you.
Yes, I think it's entirely possible. It just depends on how complex you want your model to be. In this study, we kept things very simple, but of course, you can add mass to your particles and yes, simulate the drag of the sea with a more complex equation than what we had. We kept things simple for the sake of the tutorial and to have more immediate visual results, but it's entirely possible, yes.
Great. Next question is the particle tracking tool derived from or based on parcels model? Sorry.
I'm not aware of a parcels model. I don't know what that is. I'm not sure I can answer that. But the model is, well, quite simple. I think it's a simple application of current velocity at successive time steps. So it's probably used in many models that are available in the public.
Okay, thank you. Next question is, in my routine workflow, I've generally been using R. I'm a marine biologist. How do you compare Python and R in terms of big data harvesting and processing?
Well, I don't work with R very much. I'm more used with, I'm generally using Python. So I've very rarely used R to process big data sets like this. So I'm not sure I can provide a very knowledgeable answer on this. Sorry.
Okay, I think we might be able to ask this question to Simon maybe later, who will be presenting the tutorial using R. I don't know if he might have some data to share on this. But yeah, thank you for the question. And I think this is actually the last question we received. I don't see any other appearing on the screen. No, all good. So thank you very much,
Okay.
Alexandre, for your
Thank you, Marine.
demonstration and for answering the questions. We're actually quite a bit ahead of time, I think, by a few minutes. So we will have now, we will have a short coffee break of about 10 minutes. So we will see you back at 11:10, 10 a.m. CT. So yeah, we will just take a short break and be back in 10 minutes. Welcome back, everyone. I think we are ready to continue with this session. Yes, I see Daria is here. So we will continue with a QGIS tutorial demonstration by Daria Andreevskaya, who's from Noveltis. So Daria, the floor is yours whenever you're ready.
Thank you. Thank you, Marine. And hello, everyone. I will share my screen and just make sure you can see it. Do you see it, Marine?
Yes, we see your presentation.
Okay, great. So let's start. Well, my name is Daria. I'm from Novelties. And well, as it was already presented, I'm going to show you this QGIS tutorial, which is focused on seasonal tuna habitat in the high seas. And I think it was already said a lot of times during this presentation and presentation on Tuesday that the high seas they are areas of the ocean beyond national jurisdiction, and they cover nearly half of the Earth's surface, and they host important ecosystems. They also support migratory species, like, for example, bluefin tuna, which we're gonna study today in this tutorial. These zones, they play a key role in global fisheries, and we all know that they lack governance. So even though we have pressure from fishing and shipping and other human activities on these zones, and they actually tend to increase, we still have we don't have much protection and conservation of these zones. So that's why this BBNG agreement was developed. And in the scope of this tutorial, we're gonna see how how spatial analysis of different variables was available on Copernicus Marine Service, how it can support the identification of priority of such areas and assessment of potential impacts under this BBNG framework. So for today, we're going to look at the case study of North Atlantic high seas, as you can see on this little image on the slide, and specifically on bluefin tuna, which is very representative species for Atlantic Ocean. And you can see here a little image also showing the migration of this species, and you can see that they do pass by high seas, in a zone which do not belong to any country. And we will focus this study on 2 seasons of the same year. So we'll look at the summer season of 2021 from June to September, and the winter season, which will start for us from October and will finish in January 2022. And yeah, we'll see how during these 2 seasons the ocean conditions they shifted, and how they impact the potential tuna habitat in the zone. So I will quickly show you and talk about the data we're going to use from Copernicus Marine Service. So we used 3 products. The first one is this Global Ocean Biogeochemistry hindcast, from which we will use chlorophyll A variable, which basically shows us the productivity of the ocean, so basically food for the tuna. Then we also use global ocean physics reanalysis. We'll look at seawater temperature, because tuna is a migratory species, and they depend massively on the temperature of seawater, so it's important. And the last product, which is not exactly provided by Copernicus Marine Service, it's like hosted on a platform but it's made by Marine Regions, this website here. And it's exclusive economic zones and territorial seas. So it's basically just for us to know which zones are high seas and which zones are, which zones belong to countries and different entities. And before we move to QGIS itself, just a quick note that we will use this specific plugin for QGIS, which is called the NetCDF to QGIS. It was developed here at Novelties, and the main purpose of this plugin is to facilitate the import of NetCDF files to QGIS, because basically almost all the data on a Copernicus Marine service is in this format, and the default function of default tools of QGIS that allows us to use this file format. They are a bit very bit messy and not that user friendly. So there's this plugin which is very useful. So we'll go straight to the QGIS, and that's the project already loaded, and I'm gonna just show you the like the stages of this tutorial. I'm not gonna give too much details because well, it's quite long and I don't have that much time for that. So if you want, you have a PDF file with a step-by-step procedure, and you also have a video version of this tutorial with all the steps. And well, let's start. So first of all, as I told you, there's this plugin which looks like this little icon, and here you can just ingest your data by clicking on plus and then browse to your files, or you can just drag and drop the data. And for example, I'll just drag and drop those, and also this data will be already provided to you as well on the website, so you can either download it yourself or just have a one that we give to you. So here, for example, this is our chlorophyll product here. We also have a yeah, I have two chlorophyll products. Well, whatever, we will ignore it for now. And there's this one physical with theta O, which is seawater potential temperature, and there's also seawater velocity components, which we didn't use in the tutorial, but we still loaded it for you, so you can go further and explore and do more like little exercises for yourself. So basically, if this plugin, you can just right-click on this variable and click on add layers, and it allows you to actually choose the time frames you want to load, because usually if you use the default version, like by default you add the layers to the QGIS, it will not allow you to choose the time frames. It will just load everything, and then you need to like choose like it has several bands, and here you can actually just load one or all 7, 8 actually, or whatever. I'm not gonna load them again because I already have them, but you just like choose several, you click add and close, and that's basically it. So for the product, as I told you, we loaded the chlorophyll, sorry, and it's monthly mean. Yes, it's monthly mean variable. So we have from June 2021 to January 2022, and here I will just untick the box just for you to see how it spreads, how it changes. And for example, we could see already that just very quick in summer, so in June, we would see that well, for the scale, the more green, dark green areas have more chlorophyll, and almost white ones are having less. And we can see that, for example, in June, we had a bigger productivity here, like along with Canada, and also we saw some along the coast of Portugal and also in Africa here. And we can see, well, our overall here we have not much. And then slowly we can see how it shifts. It reduces in the zones that we already spotted. See how it becomes less and less green. Then you see that from October, we basically have kind of a shift over productivity. So here we have like zone with higher productivity, a bit lower along the coast of North America. And also we can see that, well, there still have some in Africa and Portugal, and also it shifted higher towards, well, in Europe towards United Kingdom and some in France. And basically that's what we have in January. Like you can see how it's kind of shifted from up down with temperatures. And if we load the temperature, we also can see the similar trend. So first, that's our June, right? Also, same reds are higher temperatures, so blues are lower temperatures. We can see that in June we still have quite cold temperature of water here on the north of Canada. And then slowly you can see how it's kind of shifts a bit the opposite direction, we can say. We can see that here on the southern part of our study area, there's a lot of reds, like really a lot of reds. It gets warmed up very quickly in summer. And from September, we also see that it goes back down to winter, which makes sense with fresher, colder water here. And yeah, like you can see that in January we have much lower temperatures here in the south and colder on the north. So that's basically what you would expect to see, the usual seasonality of seawater temperature. And just for you, like, I don't know if how aware you're of QGIS, but you can double click on each layer and adjust your styles. It's also described in a PDF file in more details, like how you can change min and max value, change different color ramps, and also like classes and stuff to make it more representative and to also like have a better, color scheme as well. So we've seen the kind of seasonal change month by month, but what we wanted to see about seasonal tuna habitat, and for that we really need our seasonal maps. So we would create 4 maps, which are mean winter value for our SST, so for sea surface temperature, and also mean for summer and winter for chlorophyll. And that's what we did. If I just do this. So we calculated it, and we have, for example, this is chlorophyll mean for summer, so from June to September. And this one is for winter, so from October to January 2022. And exactly, we could see that the productivity did shift. Oh, sorry, that's not this one, that's this one. And to do so, we use a raster calculator function, which you can type here in the search bar in the processing toolbox. I already have it here because I used it, but if you just continue, you will see it under raster analysis. So it's here. So basically, this is a very, very useful tool. It allows us to calculate, to work with raster layers. They are raster layers because they are consisting of pixels. And it allows us to basically have different combinations of different layers and have more information and like perform analysis. That's a very, very useful tool. So basically, in input layers, you usually choose the layers you want to work with. For example, for chlorophyll main summer one, we would choose June, July, August, September. Yes, okay. And then you would paste an expression here, or you can click on this one and actually made it yourself. So as it's a mean one, so it's basically sum of each layer. Oh, well, I don't. I just added it twice. Well, the second layer and the third and so on. And then you like close it and divide by like 4. Well, here it's by 2, but we usually do by 4. I can even like copy paste it maybe very quick from the expression I used in PDF file. So it looks like this kinda. You click on OK, then you save it to a temporary file or to temporary file is gonna disappear as soon as you close your project in QGIS, and just a file on your computer will stay and you can use it after. So then you click on run and it will calculate and create a new layer like this, for example, for winter, as I said, and this for summer. And the same is for sea surface temperature or seawater temperature for summer, like this is a mean one. So the combination of 4 months from June to September. Here we can see a very red, very high temperature zone here, and well, less cold in north. And for winter, we can see well, what we're supposed to see, colder water here and warmer water down here. So that's it for seasonal maps, which is very useful to have. And then what we created them for is to actually map our potential tuna habitat. So for that, we would need, again, raster calculator and our 4 layers we've just created. And we would need some specific threshold. So this can be a bit like, you can play with them. For example, that can be also as an exercise for you. You can play and decide on different thresholds to see also how the tuna habitat would shift if we would take into account different thresholds. But we decided that, well, we chose that the ecological preferences for this type of fish is a sea surface temperature between 15 and 25 degrees, and the chlorophyll concentration should be above 0.15 milligrams per cubic meter. So these ranges will represent the conditions that support feeding and migration in the open ocean. And for that, again, in a raster calculator, I'm not gonna input select input layers. I'm just gonna go straight to the expression. And the expression we used, I'm gonna show you. So we would need to create 2 more maps. One is tuna habitat for summer and one for winter. So for summer, it would be this. So basically, we say that chlorophyll main concentration in summer should be above this specific value. And at the same time, we want the sea surface temperature to be above 15 degrees and at the same time below or equal to 25. So basically, that's our expression. And for the winter is basically the same, just each summer layer is replaced by winter one. So that's it. And it will give us something like this. Let me, something like this for, what is it? It's winter. It's winter habitat, like this. Well, usually, if you double click on it, it was already adjusted the style. So this is still a raster layer with only with pixels of 2 types. So 0 means this conditions did not apply in these zones, meaning it's a not good potential habitat, and 1 means that it's a good one, and all the conditions did meet at these zones, at these pixels. So we basically colored them in blue layer for blue color, sorry. And for 0, we just made it transparent, and obviously you just double click on this little color and then you change it here. So that's it. Like this, we just see better, overlapped with our map. The potential habitat for tuna in winter. So we can see that, for example, it's goes, well, we see some zones that are under the jurisdiction of some countries, but also we can see that a big part of it is under high seas, which is exactly shows us why it is important to have a specific rules and more protection of these zones. And if we look at the summer one, which is colored in red, and we also made it a bit transparent, we can see that it actually changed quite a lot. Also, we can see that it shifted more to the north, which makes sense because as tuna prefers quite cold water, though, between 15 and 25, let's say. In summer, this area down here, like we saw in summer, which is this one, we see that below, on the lower part of this zone, it's very hot, so it doesn't like that, and the fish it moves higher toward the north, and the same for the winter. Sorry, up. And for winter, it moves a bit lower because, well, it becomes too cold higher up. So that's it. And for that, we can, as I already said, we can see that the big part of the migration routes over potential habitat, it does stay in a high seas. And we also can see that even though that's 2 different seasons, like winter and summer, we can see that there are zones that are overlapping for both of the seasonal maps. And next, we will look exactly on the overlapping of these zones with zones that are actually under national jurisdiction, so the part of the seas that belong to some countries. And for that, we used this layer I told you about, which is also available on Copernicus Marine Service. And this is this layer, which is very heavy, very bulky, because it's literally covering the whole globe. And it consists of, well, small little polygons everywhere. You can see, well, it takes some time to load. And of course, we don't need all that. We just have a specific zone. So we would need to cut it. But first, we needed to fix it because, well, in QGIS, sometimes when you work with vector layers, and this is a vector layer, you can see that there are geometries, not pixels. Sometimes we need to fix it first because there might be some incompatibilities inside. So it creates this layer, which is going to look exactly the same, like we won't see much. And for that, you go to Fix Geometries tool, which basically allows you to choose the layer, and then you run it, you close it, and it kind of adjusts some incompatibilities that we might not see, but QGIS analysis might encounter some problems later on. So we do it before working with this layer. And what we wanted to do with this layer, we wanted to clip it, so to have our zone. And for that, I think it's not called clip though, I think it's called extract. I need to verify it because we have a lot of different tools. Yes, it is extract or clip by extent. This one, which is under vector overlay tab. And it allows us to choose our layer and then an extent which you can, well, type yourself, or you can also calculate it from the layer. And for example, I just chose any chlorophyll layer and then run it and close it, meaning that, well, we saw that we had a specific area for the chlorophyll, sorry, or what else? Temperature layer. So we basically used the boundaries of this layer to cut this one. And as a result, it will give us something like this. I will hide this one and maybe this two as well. It will give us this, but not exactly, because I have a little filter sign here. If I click on it, you can see that there is a filter applied, which I will remove. So when you cut it, when you clip the layer, it will look like this, also including the high seas. You can see that this is a high seas and this is the areas belong to countries. And if you double click on it, you can change its opacity again, like I did. Well, it will just reapply it. And to filter it, just to see the zones, like to make the high seas not shown, we can filter it by right-clicking on it. We go to filter, and we pay this expression, which says that this value should be not equal to 0. And it will give us what we need. And I will explain now why we used exactly this expression. So if you right-click on the layer, on a vector layer, on any vector layer, you have an attribute table, which basically has all the geometries which are loaded in this layer. So for us, it's a lot of polygons with different columns with different information. And here we can see this value, this column we used to filter. But first thing, there's also like these regions, marine regions that are stated here. And we just looked through to see if there's something called high seas. And there should be high seas, which I do not see. Maybe I'm not, did I already filtered it, did I? Ah, yes. Yeah, that's why. Okay, I will remove a filter and no, not this one. And I will again go to attribute table. Yeah, okay, now should be high seas here. I'm really not seeing them. Ah, they're here. So there are high seas, like there are 3 polygons that says it's high seas of this, and this zone. And you can see that they have this column equal to 0. So that's how we decided to filter our layer. And then we intersected with our habitats. Again, it's just another way of like visually spot the zones that are high seas. So it's basically all the zones that are not green. And we can see that many parts of tuna habitat, potential tuna habitat, still lays in a country like country waters, and some in the high seas. And the last little exercise was just to show you a little external data, which is called Global Fishing Effort. It is provided by a website which is called Global Fishing Effort, if I'm not mistaken. Well, the link is also in a PDF file. So it basically gives us a raster file with pixels in which there been fishing activity detected. So vessels, like shipping vessels, fishing vessels, sorry. And pixels are colored according to the hours of this activity spent in this specific zone. So the more red, well, it's not very clear from here, but more orange pixels means that there are more fishing activity in hours than blue ones. And we can see that mostly fishing still happens along the coast, and that's true. I think around 90% of all the fishing happens along the coast, and not that much happens in the open sea. And this one was for summer, so it's accumulated all the accumulated hours for the June, September. And we also have a one for winter, which is this one. And again, you can see that we still mostly fish along the coast, not in the ocean. But you can see the difference between them too. And you can see, for example, in summer, there are more activities in the open ocean. In winter, it's kind of more reduced. But also we can see in winter, there's a spot here that was not present in summer. But this is, of course, all the fishing activity, not only tuna, like whatever species, but this is just an example to, for example, we can overlay it with summer, this one, or no, maybe winter would be more representative, I don't know. Yeah, we can overlay it just to see that, yeah, of course, it's still the fishing happens in the coastal areas, the zones under the jurisdiction, the national jurisdiction, and there are potential habitat for tuna there, for example. But also there's overlap in the high seas. So even though we do not fish that much in high seas, some of this activity still happens there, and there's no jurisdiction, there's no protection of these zones, and that is why it is important to make such rules to specifically protect marine species that might be not very well treated, let's say, in these areas. So that's basically it. That was a bit hectic maybe because I don't have much time, but I hope you learned something new. And of course, you can explore further with this tutorial. Like in a PDF file, there's a little exercises to go further chapter in which you can see our propositions of how to make this tutorial like more rich, let's say, and more long or more in details. So don't hesitate to go and check it out. And I am ready to answer some questions. Thank you for your attention, though.
Thank you, Daria. We received a few questions for you.
I will stop my share. Yep.
Okay, so if you have any other question for Daria, don't hesitate to post them in the Q&A section. But the first question we received is how to find a world fishery distribution map using Copernicus Marine to produce it.
That's, well, on the Copernicus Marine service, there is no data available for world fishery or for fisheries at all. It's up to you to search really in specific regions. It's also not very mean, in my experience, it's not very common to know exact locations for fisheries. I guess they do not really share it. Maybe it's not very safe for them. I really don't know. But I think there are sometimes some databases you can find in the internet which might at least give you some approximate locations. And this one, this layer which we used, which is Global Fishing Effort, that's it's available online. It's free, and but I think it's only for ships, so it's not for, it's like for vessels, so something that moves. I don't think it's for like fisheries when we really grow fish and then like use it. So yeah, but already I think this website, you can also check it. I think it's very, very, very nice addition to study such topic.
Okay. Actually, yeah, and just to add to what you just said, Daria, I just wanted to highlight that on the Copernicus Marine website, we have data like ocean physics and biogeochemical data that can be useful for fisheries, but exactly, we don't provide a map of them. And I just saw someone in the who added a comment about the fishing effort map that was used in the in the tutorial, and this person said that the data comes from Global Fishing
Yeah,
Watch, but yeah, it's not. So
it
yeah,
is indeed, yeah.
you can access this.
Yeah, but as I said, yeah, the link and yeah, all the data I used will be also uploaded on event page. So yeah.
Okay, great, thank you. Next question is, what does this EEZ intersection zone represent, and why is it useful?
So this layer means exclusive economic zones. So it's basically exclusive economic means that these areas, they belong to a specific country and they are protected by this country, and there are laws of this country that applies in these zones. So which is, for us, it is useful to see which zones are already under some jurisdiction, which means that supposedly the like fishing activity there is more controlled, it's more like it's more protected, let's say. So we know that's not going to be some shady business happening there. But for the high seas, which do not belong to any country, they have no jurisdiction, and that's why the topic of this tutorial is the BBNG agreement, which is why it's important to have such agreement, is because, well, there are no laws basically. So anything is allowed in the high seas because it doesn't belong to any country and there's no one regulating it. And that's why it was interesting to see the human impact, human pressure on these zones, to know if we really, like, to see that we really have to protect these zones, because sooner or later that might be like something bad can happen in these zones, because we just don't have we don't have regulation in these zones.
Okay, great, thank you. We have 4 more questions. We will go through them quickly before we go to the last tutorial to try and respect the agenda. The question is, rather than simply defining upper and lower bounds of a species preference to some environmental variable to get binary habitat suitability, is it possible to define an environmental preference function to then get a probability distribution of habitat suitability?
That's a very complex analysis already. For sure, I mean, if you have a specific function, right? I'm not aware of a bell curve specifically, but if you have a specific function which uses variables, for example, which we loaded, or some other variables also as well. If you have a function like with different, like how to say, with conditions, with relations between them, of course you can use again raster calculator, and it gives you maybe better representation. Also, there is a way, yeah, from the raster calculator, you also can make a classification maps. So it's not going to be like just binary, like yes or no, but it also will show you, I don't know, for example, it could be yes, no, and then, I don't know, probably yes, probably no. So like you can have more classification than just like binary, yes. And it will depend on the like percentage or on the threshold as well. So yeah, of course, it's possible. Just well, need more data maybe for that.
Okay, thank you. Next question is, oh, sorry, I made it disappear. But the question was, what is the best
Yeah.
output?
It was TIFF, I think,
GeoTIFF, yeah.
ASCII, yeah.
ASCII.
For QGIS, I think it's better TIFF. I think so. I think ASCII it's also possible to import and work with in QGIS. I don't usually do that, but I mean, TIFF is quite popular format, so maybe it's just more like more spread. But yeah, I don't know what's better between them, but for sure TIFF like used widely.
Okay, thank you. Next question is, what is the impact of upwelling on the migration of tuna fish distribution?
Oh, this I cannot really answer, I think. But well, again, upwelling happens in the coastal zones, so already you need to like zoom more on the coast. And here we didn't have this; we had a bigger scale. But yeah, I mean, upwelling brings more nutrients, right? So might be good for fish sometimes. Too much nutrients might be not very good. So yeah, that's another study. That's maybe also a good idea for us to make a tutorial on that as well in the future.
Yes, that's definitely a good additional
We're gonna note
exercise to include. Okay, great. And last question, and this time I'm not, okay. If the fishing activities are recorded based on the moving vessels, how are we sure that the data is actually correct, as some vessels aren't for fishing?
Yeah, that's a good question, and that's well, on official website of a Global Fishing Watch, I think it's called, right? You can see exactly, they have a full article about how they measure this activity. How do they separate between vessels also? And yes, indeed, vessels they also move. So yeah, you need to know when they even, because I think they do have a separation between vessels that like fish when they like anchored and they stay on the same place, and the fishing vessels that do, I don't remember how it's properly called. You know, when they move and they just um, have a big net behind attached, and they just gather whatever comes into this net. I think they have a distinction between these two. So I suggest you just to go to this website and read more about it. They have a very good explanation, really. But I did not get very into detail, so I cannot really help you on this question.
Okay, well, thank you very much for your presentation and for answering all these questions.
Thank you.
We will now go to our last speaker of the day, who is Simon Millet from Noveltis, and who will present our tutorial. So I can see you, Simon. Welcome, and the floor is yours whenever you're ready.
Yes. You see my screen?
Yes, we do.
Yes. So, hello everyone. My name is Simon Millet. I'm a scientific engineer at Noveltis in France. And in this tutorial, we will show you how local cement can be prospected area for the BBNG agreement. So first, during this tutorial, we will explore the NetSD file from the Copernicus Marine service. Then we will make a basic plot of temperature and then see the variation of temperature and salinity over time. Then we will see the variation of geochemistry parameters and finally the current. So for this tutorial, we focus on the local cement located in the High Sea of the Northeast Atlantic, which it is outside any exclusive economic zone. So this area has a major ecological importance because there is deep sea habitat like corals, fish that needs a stable condition to survive and reproduce. So in this tutorial, we will use Copernicus Marine data to see how the area is are stable through the years, providing a safe habitat for biodiversity. So the tutorial will combine a monthly average, showing difference between extreme value and time series over months. And this approach demonstrates how Copernicus data can support the scientific identification, and the reconnaissance serve as an illustration example only. So the reconnaissance is located here in this area, in the northeast of the Atlantic. So first, we need to have the different libraries to use these tutorials. So we need ggplot2, that is for creating graphic. Dplar, it is a library for manipulating data. rcolorbrowers, it is a library for color palette in plot. netcdf4, it is for netcdf file format. Gridesa, it is for arranging multiplot on a page. Lubridate, it is to manipulating datetime data. Scrolls, it is for aesthetic option, and gquiver to create quiver plot. So first we load the libraries, and if you use another support, you can install all the libraries thanks to this link. So the data during this tutorial, we will use two different data dataset that is available in the Copernicus Marine data store. You have the link here. So the Copernicus Marine service is free and can and deliver high quality information of ocean condition, near real-time forecast or reanalysis for different parameters. So for this tutorial, we will use the global ocean physics reanalysis in the North Atlantic Sea. So here it is the latitude and longitude that we have used at different depths, and the variable current, temperature, and salinity, that is the variable that we use in this tutorial. And we use a monthly average from January 2010 to November 2025. And the second data set we use, it is the biogeochemistry cast. It is in the same spatial region, and there are different variables, but in this tutorial we specific use the phytoplankton. So the files are already downloading in this tutorial, but if you want to download it, you have all information here, and you can use your username and password to download the data. So first we will explore the netcdf file. So it is physics data. So first we set the path of the netcdf file. Then we load the netcdf file and print information about the netcdf. So you can see there are different variables. There's three variables: salinity, temperatures, and the temperature at the seafloor. There is 4 dimensions: time, depth, latitude, and longitude. And here it is a global attribute to have more information about the data set. And here we load the variable that want to study. So we need latitude, longitude, time, and depth. So we use nCvarget function, and the temperature and the salinity here. It is possible to see the dimension of temperature and a value for a specific longitude, latitude, depth, and time. So you can see here the dimension and the specific value of temperature. And we do here it is very important because we convert the time value that is a number to a date thanks to the function as POSIX here, where we put the origin. It is in January 1970. It is noted in the characteristic of the dataset here. So now we can see that the value here, it is a date. And here it is for saving memory. So now we will do a map of temperature. So first we define the figure size. Then we create a data frame. So a data frame of temperature dependent of longitude and latitude. And we choose the index of depth and the index of time. So here it is 1 for the depth, that indicate it is at the surface, and here the index of time. And we can see the data frame here that the temperature dependent only of longitude and latitude. Here we create the directory figure, and then here we plot the map of the temperatures. So we use ggplot, and then we use GeoMorator to put the data and the data frame we have created. Here it is a general option for color scale option, and here title and subtitle. And you can see the surface temperature on the area of interest on for March 2010. And you can see the temperature is globally stable between 8 and 12 degrees. But the area of interest is VES coordinate. So it is the box here. So we do exactly the same figure, but we see the area of interest here. So the temperature is lower in this area, and it is stable. So now we will see the variation of temperature and salinity in this area. So first we construct a new data frame depending here of the longitude, latitude, time, and depth. So it is a large data frame. And we have a value of temperature and salinity. Then we subset the data frame to have only the area of interest, so the box that we have seen before. And we add the corresponding months. So if it is 1, it is in January, and if it is 2, it is February, etc. And you can see here the data frame. So there is the value of temperature and salinity that dependent of longitude, latitude, time, and depth. And here the column of the corresponding months. So to save the memory, we delete the previous data frame. And here it is a code that we do a statistic. So we use the previous data frame, and we group by longitude, latitude, and depth. So for a second longitude, latitude, and depth, we do the mean of temperature. We calculate the standard deviation of temperature and the difference between the percentile 90 minus the percentile 10. And we do exactly the same for salinity. So the percentile 90 indicates that 90% of all the value are below the value. And we can verify the data frame. So you can see here there are different value for the mean temperature, standard deviation, different. that is only dependent of longitude, latitude, and depth. So now we will map the statistic. So at 8 meters of depth, so we filter this data frame and we create a plot. So it is approximately the same plot that you have seen before. And we can see the temperature, the difference of temperature between the percentile 90 and the percentile 10 over the 15 years period. So we observe a temperature variation between 4 and 6 degrees. So at 900 meters of depth, this indicates a certain degree of stability, of thermal stability, because the range is not very important. And now we will do the same plot for salinity to see the evolution. And you can see different pattern of salinity with temperature. And the salinity range is between 0.15 to 0.35, indicate a more stable condition for salinity. So with temperature and salinity, we have seen that at 900 meter of depth, the temperature and salinity are stable. That is important for biodiversity. Now we will see other variable. We examine the evolution of phytoplankton. So first we load another data set. So it is approximately the same code we have seen before. We create a data frame and we subset for the area of interest, and we add the corresponding month column. And then here we do a statistic. So we group by longitude, latitude, depth, and month. So, and we do the mean of phytoplankton. So we have a value for each month, for each longitude and latitude, and for each depth. So you can see the data frame. We have a mean of phytoplankton depending of longitude, latitude, depth, and month, not of the time. And here it is a function for mapping the data frame. It is to avoid to have the same code many times. And we create the maps here for different months and different depths. So here we use one index of months for January, here April, July, and October. And we put only on the surface because the index of depth is 0. And you can see the phytoplankton concentration at surface for different months. And we can see there is a large concentration of phytoplankton between approximately 0.5 to 1.5 millimole per meter cube. And there is a seasonal variation, especially in summer, because the sunlight is more important, so create more photosynthesis and so more phytoplankton. So we do the same plot at 900 meters. And you can see that the concentration is less important, but the concentration is already present at 900 meters. That is important for the biodiversity. And the large concentration of phytoplankton at surface is very important because it is a stable condition for food ecosystem and for the different level, because the phytoplankton is important for species at the surface and then create large nutrient for at the depth. Now we will see the variation of, we'll see a current. So current is important too because current propagate eggs for the corals or fish and propagate the life at deep sea. So here we first load the data set, we create a data frame, and we create the column of the month. And then here we do the mean of current for the eastward current and northward current, and for the value of the current. And here we do we use this data frame, but we filter with different level. So the level of 20 meters here, and for January. And we, sorry, I think I forgot to run a sales. Yes, I forgot to run this sales. So it takes a few seconds. So here we plot the map of the current with the geom tile and geom quiver to display the arrow of the current to see the direction. So here it is the current in January at 18 meters. So you can see different pattern. And the current is moderate, is not very low, but not very important too. But it is good for biodiversity. So, but it's important, it is to see the current at different level. So for this, we will see the current at different level and during the different months. So we will looking the variation at a single point. So here it is the coordinate that we want to see. And we create a data frame dependent of the index of longitude and latitude that we want. And here we create a vertical grid with regular vertical grid for each 1 meters to avoid a blank in the figures. And here you can see the figure of current. So depending of the depth here and the different months. And you can see in winter, the current is more important. And at the depth, the current is less important, but at the surface. Nevertheless, the speed remain moderate, that can propagate different eggs. But it is important to have current to coral growth and overall marine biodiversity. So now the tutorial is finished. If you have questions, do not hesitate.
Thank you very much, Simon. We actually have a few questions, and the first one, maybe I was going to say you can continue sharing your screen because we have one that is, could we please see the variables used for the variation of currents again? If you could show them on your screen. Thank you.
Okay, so the variables that we have used, it is the the current here, so the latitude, longitude, time, and depth, and we use the eastward current and the northward current. Then we create the norm of the current thanks to the eastward and northward current.
Okay, thank you. Actually, for now, we haven't received any other questions. So if you have a question for Simon on this tutorial, don't hesitate to post them in the Q&A section. We're just going to wait for one minute, just in case someone is typing at the moment. Okay, I don't see any question coming in the chat either. That happens sometimes. Okay, well, I don't think we have any other question for you. So thank you very much for your presentation and this demonstration of tutorial. Was very interesting. And I think, yeah, definitely not getting any questions. So thank you, Simon, once again. And I will now close this session. So let me share my screen.
Okay, bye.
Thank you, Simon. Okay, so just wanted to share with you some information before we close this session today. This is just one last reminder about replays and polls. You'll find both of these on the event website through the menu at the top of the page. And we will also send you a link, an email with a link to the replay and to the poll once the replay is available online. We also recommend that you check our YouTube playlist for webinar replays. You'll find replays from the past 2 to 3 years, and you'll also, replays of all the training sessions that we had. They're all freely available, obviously, it's on YouTube. And you can also find out about all the upcoming and past events from the Copernicus Marine Service on the Copernicus Marine website. You just need to click on the Events tab on the Events page in the top menu. If you enjoyed today's session, we encourage you to help us spread the word about these sessions by sharing your experience on social media. Don't forget to tag the Copernicus Marine Service if you do so, and this way we can interact with your publication and actually see it. And finally, I just wanted to let you know about the next event we're organizing, which is a 2-half-day online session focusing on helping participants turn Copernicus Marine data into engaging visual stories. It's a great opportunity to explore the value of ocean data, boost your data visualization skills, and contribute to a real-world publication, because you will get the chance to have your work featured on the cover of the 10th edition of the Ocean State Report. So this is a really great opportunity to hear from designers on how to create interesting data visualizations. And you can find all the necessary information about this on the event website. You just need, once again, to go to the events section of the Copernicus Marine website, and there you can find the event page and register directly on here. So we are reaching the end of today's session. Thank you very much for joining it. I wish you a great rest of the day, and thank you again. Bye-bye.